Assalamualaikum warahmatullahi wabarakatuh, and good day to everyone that's watching, especially to Sima Hassan. And today my team will present about automatic clothes dryer for BMIP 2343 control system presentation. And let's go to our teammates. First of all, representing me, Farunda bin Hamdan, and my other teammates, Muhammad Hafiz, Muhammad Ilman, Muhammad Akmal, and Bashira Arifah. So without further ado, I will pass down to our first presenter, Brother Muhammad Hafiz.
Assalamualaikum and hi everyone. My name is Muhammad Hafiz bin Amirullah and I am the first presenter for our group. Our group presentation is about automatic cloth dryer second order system. In this video, I will explain the introduction of the application and the control system implementation. Let's begin with the first part, which is the introduction of the application. An automatic cloth dryer is a machine used to remove moisture from clothes by using heated air and drum rotation. In modern dryers, the drying process is controlled using temperature and moisture feedback. This helps the dryer dry the clothes more efficiently and prevent problems such as overdrying and underdrying. This system is considered as a second-order system because it involves two main processes. The first process is heat or storage in the heater and air inside the dryer. The second process is moisture evaporation from the clothes. These two processes affect how the dryer responds during the drying operation. Next, I will explain the control system implementation and mechanism. The automatic clothes dryer uses a closed-loop control system. First, the user selects the desired drying level, such as normal dry, extra dry, or iron dry. Then, the sensor detects the actual temperature or moisture level inside the dryer. The sensor sends this information to the controller. The controller compares the actual value with the set point selected by the user. If there is an error, the controller will adjust the heater output. When the clothes reach the desired dryness level, the system will reduce the heat or start the cool down process. This makes the dryer more automatic, safe, and energy efficient. This is all for my part. I will now pass the presentation to the next presenter. Thank you.
Hello, my name is Bashira. I will explain about automatic cloth dryer block diagram. The selected second order system for this project is an automatic cloth dryer temperature control system. The purpose of the control system is to maintain the drying temperature at the desired value so that the cloth can be dried efficiently without overheating or damaging the fabric. The system operates as a closed-loop control system where the desired temperature set point is compared with the actual temperature measured by a sensor, producing an error signal that is sent to the temperature controller. The controller then adjusts the heater actuator to supply heat to the dryer and heating chamber, and the resulting output temperature is continuously measured and feedback by the sensor to maintain the temperature. Close to the set point. The block diagram of the system is shown below. Input reference. The input of the system is the desired drying temperature selected by the user, for example, 60 degree. This value acts as the reference signal for the controller. And the controller compares the desired temperature with the actual temperature and generate a control system to regulate the heater operation. Actuator. The actuator is the heating element which converts electrical energy into heat based on the controller's command. Process. The process of plant consists of the dryer chamber and the cloth being dried. Heat produced by the heater increases the temperature inside the dryer. Output. The output of the system is the actual temperature inside the dryer chamber, which should follow the desired temperature. And feedback, that's temperature sensor. The feedback element is the temperature sensor, which continuously measure the actual temperature and send the signal back to the controller. This allows the system to automatically correct any temperature error and maintain stable operation. And the next slide is first, the block is the forward path combined in series to obtain GS equal 25 over S plus 7. Since the feedback path is unity feedback, HS equal 1. Using the closed loop transfer function formula, we obtain the final transfer function is TS equal 25 divide S square plus 7S plus 25. Because all coefficients in the characteristic equation are positive, the system is stable and suitable for temperature control in the cloth dryer. For this section, I will explain the transfer function of the cloth dryer temperature control system. The system is modeled as a second order transfer function which is given by GS equal omega n square divide S square plus 2 zeta omega ns plus omega n square. In this project, we assume that the natural frequency omega n is 5 radian per second and the damping ratio is 0.7. First, we calculate omega n square. Omega n square equal 5 square equal 25. Next, we calculate 2 zeta omega n. 2 zeta omega n equal 2 times 0.7 times 5 equals 7. After substituting this value into the standard second order equation, the transfer function becomes gs equal 25 divided by s square plus s7 plus 7s plus 25. So the final transfer function for the closed dryer temperature control system is gs equal 25 over s square plus 7s plus 25. This transfer function will be used for further analysis including peak time, settling time, percent overshoot and MATLAB simulation. That is all for the transfer function section and from me. Thank you.
Assalamualaikum. My name is Muhammad Iman bin Abdul Halim. So in this section, I will explain the calculation of peak time, settling time, percent overshoot and the MATLAB simulation of the automatic closed dryer control system. The transfer function obtained for this system is G of S equal 25 divided by S square plus 7S plus 25. So this transfer function represents a second order system with a natural frequency of 5 radian per second and a damping ratio of 0.7. So using the standard second order system equation, we calculate the threshold response specifications. First, the peak time, which is Tp. The peak time is calculated using the formula pi divided by omega n multiplied by square root of 1 minus zeta square. Substitute the value of the peak time obtained is approximately 0.8 second. Next is the settling time, which is Ts. The settling time is calculated using the formula 4 divided by zeta omega n. So after we substitute the value of zeta equals 0.7 and omega n equals to 5, the settling time is 1.14 second. So the third parameter is percent overshoot. The formula used is e to the power negative zeta pi divided by square root of 1 minus zeta square and multiplied by 100%. So after calculation, the percent overshoot is 4.60%. To verify the analytical calculation, MATLAB software is being used. First, the transfer function is defined using the tf command, then the step command is used to generate the step response of the system. Finally, the step info command is used to obtain the system characteristic automatically. The MATLAB command used are shown on the screen. After running the simulation of MATLAB, produce the step response graph and calculate the threshold response parameter. The MATLAB results are peak time equals 0.882 second. Settling time equal 1.2 second. And the percent overshoot equal 4.60%. So after comparing the MATLAB result with the manual calculation, the value are very close. The small difference are caused by rounding during manual calculation and MATLAB's higher precision. Therefore, the MATLAB simulation successfully validated the theoretical calculation for the assignment. So that's all from me. Thank you.
We're back to me, Fadan Ryan, and right now actually, I will present about the MATLAB and Simulink comparison. So first of all, you can see on the left side here, top left side corner here, this is the assembling circuit that was built identically to our block diagram. And on the left here, we have the MATLAB output, the step response graph output. And on the right side, we have the Simulink graph output. So next I will explain about the step response graph output. First of all, we can see there is a rise time of 0.425 over here. So this is the rise time, the TS, and then we get to the peak time, showing the things that we're gonna highlight here is the overshoot, the percentage of overshoot, or percentage OS, which is 4.6%. And we have the peak time here, TP, 0.882 seconds. Next, we can see over here, this is the settling time from the graph. So we can see there's a rise, peak, and settling time. The settling time is 1.2 seconds, and at the end there we have the steady state value. The final value is 1. Here, as you can see on this y-axis, the value is 1. And so this is the comparison. This is the manual calculated value, and this is the MATLAB output, right? As you can see here, the percentage of overshoot is identical, 4.6%. Here, 4.6%, and compares to Illman's. Second of all, we have the peak time, 0.88 seconds compared to the manual calculation. However, on the settling time, we have a minor changes or minor difference, let's say that, calculated value between calculated value and the MATLAB output. We have 1.14 seconds here, and the MATLAB has 1.2 seconds, right? MATLAB is a high precision solver, so they will count a lot more accurately based on the decimal places. I will pass down the presentation to one of our member, Muhammad Akmal, to present about the stability of the system furthermore and the steady state error calculation. Thank you very much.
Hello, Assalamualaikum. Today I want explain about stability system. The stability system, I collect data for stable from damping ratio. The damping ratio obtained is 0.7, seeing the value between 0 and 1. The system is classified as an undamped second order system. An undamped system produce a small oscillation before reach the steady state value. The oscillation gradually decrease because of the damping effect. MATLAB graph also shown a small overshoot of 4.6% and a setting time of approximately 1.2 seconds. Therefore, the automatic clothes dryer system is considered stable. Next, steady state error analysis. The automatic clothes dryer is classified as a type 0 system because it does contain a pole at the origin. For the step input, the position error constant KPE is equal to 1. Therefore, the steady state error is 0.5, which means the system still has a finite error. For the ramp input, the velocity constant kV equals 0, causing the steady state error to become infinite. Similarly, for the parabolic input, the acceleration constant Ka is also 0, resulting in an infinite steady state error. Therefore, the system can track a constant input, but it cannot accurately follow continuous change input such as ramp and parabolic input. In conclusion, the system is stable because the damping ratio is positive and the system undamped. Itu saja.
Back to me again, and this part is the discussion. So first of all, the project successfully evaluated the closed-loop temperature control system of an automatic clothes dryer using an assigned natural frequency of 5 radian per second and damping ratio of zeta equal to 0.7. This yielded the characteristic transfer function here. So that came from this transfer function equation here, right? Step response analysis. The manual calculations correlated exceptionally well with MATLAB. So we do the comparison last time, and we can see it's really close to identical, I would say. Both from the MATLAB and the manual calculation has achieved 4.6%. So it has proven the percentage of overshoot is 4.6%. The peak time, the calculations, and the MATLAB gave the same thing 0.882 seconds, and the settling time, manual calculation estimated 1.14 seconds, while MATLAB recorded 1.2 seconds. The minor deviations between the analytical and simulated results are strictly due to decimal rounding in the manual steps. The stability and steady state error that was done by Akmal with the damping ratio of 0.7, we can see that, or we are aware that the system is an underdamped system because zeta is lower than zero, and I mean zeta is higher than zero and lower than 1. That proves it's an underdamped system. The system satisfies standard stability criteria, meaning the transient oscillations decay rapidly and the system is inherently stable. There is no pause in the open loop transfer function. The system is classified as a type 0 system. It tracks a step input constant reference temperature with a finite constant steady state error, ESS. It yields an infinite steady state error, which is infinity, for RAM and parabolic inputs, meaning it cannot track continuously increasing or accelerating temperature targets. Okay, so this is our conclusion. This assignment successfully analyzed the second order closed loop system, temperature control system of an automatic clothes dryer. High accuracy agreement was achieved between manual mathematical derivations and computational MATLAB simulations, validating the analytical framework. With a damping zero of 0.7, the system demonstrated a stable underdamped response with minimal 4.6% of overshoot and a fast settling time of 1.2 seconds. And the steady state analysis confirmed the dryer is a type 0 system, meaning it can reliably track a constant target temperature with finite error, but cannot follow RAM or parabolic profiles. And all core objective of the control system assignment was fully accomplished. So, that is all from us. Thank you so much for watching our presentation, and inshallah I'll see all of you soon. Thank you so much. Goodbye.